All right, so in this video, we're going to look at limits in two or more variables. And we're going to start with a quick review of limits in one variable, because our main idea with limits in two or more variables is we're going to choose a path to the origin. That's typically what we worry about, to reduce the function that we're dealing with to a single variable. And then all of our one variable techniques are going to apply. So recall that essentially if the limit of a function is equal to L, that means that as x gets closer to this value that we're targeting, closer as in sufficiently small, that implies that the difference between the function and the limit, the function value and the limit value, is also very small, and usually in a predictable way. Now, in multiple variables, we're going to be dealing with two-dimensional versions of this or three-dimensional versions of this. So we're going to be dealing with distance functions rather than absolute values. So the formula is going to be a little bit more complicated, but the idea is still basically the same. As our value that we're approaching, our point in space, gets smaller and smaller, then the distance from the function to the limit is also going to get small. Now, if the function is not continuous, then we will use various techniques. Again, we're reducing our problem to one variable, so the same techniques that we used in one variable could presumably apply in the multivariable case, depending on how the function gets reduced. So recall that we can factor and simplify our expressions. So if we end up with something that has common factors, we can reduce it, get rid of the division by 0, and then evaluate the function from there. We can rationalize denominators in order to get the division by 0 out that way. We may encounter special limits, that the ones that we memorize and then eventually proved using L'Hopital's rule. We can use log tricks also. Now, these are somewhat uncommon in the multivariable case because there's enough other weird stuff going on. But again, kind of keep it in mind. And of course, L'Hopital's rule does not apply in the multivariable case. It applies in the single variable case. But because we are going to be using our techniques, our strategies, in order to convert our multivariable problem into a one variable problem, then we will have access to this also. Now, let's look at the formal definition in the two variable case. So we have our function of two variables. It is approaching a point in the plane. And then what we're saying again is the distance between that point in the plane and our pair of x, y coming from any direction along any path. If it's sufficiently small, then that means that again, the Euclidean distance between the function value and the limit value is also small and getting smaller. And again, in a controllable way. And of course, you can extend this to 3 dimensions. If you have a function of x, y, z, then you would have 3 things under your square root, again, Euclidean distance, to calculate this multivariable dimension. But again, the idea is basically the same. Here's the 3-dimensional case. But again, you're within a circle or within a sphere around the point that you're targeting. And the difficulty with the 2 and 3-dimensional cases is that there's a lot of different things that can happen. You may have different paths that you can approach going to the origin, and you need to account for all of them. It becomes very difficult sometimes to prove that the limit exists in multiple variables because of all of those different paths that you can take to the origin. It's actually often easier to prove that the limit doesn't exist. And so that's one of the things that we're going to be talking about, is essentially, how do we know that the limit does not exist? How can we find the evidence for that? Now, we've seen in the case of the one variable problem where the limit actually doesn't exist, is not just division by zero, but after we apply our techniques, we have to actually get like two different values, maybe positive and negative infinity on different sides, or maybe if we come from the right, we get to one value, and if we come from the left, we get to another value. That's the kind of thing that we're looking for. If we choose different paths toward the origin, do we always get the same value, or are we going to get different values depending on the path that we take? So let's look at some easy examples before we go to the harder ones. So sometimes it's only going to be undefined in one variable, and we can use our techniques that we did in the one variable case to simplify this. So in this example, sine x over x going to 0, we can actually separate it out, the sine x over x going to 0 and the limit of y going to y. This doesn't, because we've separated them out separately, we actually know that the path doesn't particularly matter. Anytime the limit of x goes to 0 of sine x over x, we get 1. That was one of those special limits, or you can use L'Hopital's to prove this. And then the limit of y as y goes to 2 is just 2, because it's a continuous function. And so you end up with 2. Again, take advantage of it when you can. The tricky ones are usually going to be the points that go to the origin, where you can't do stuff like that. So again, in this case, if we plug in the origin, the 0, 0, our target, we get division by 0. You can rationalize this. You can put in a dummy value, so like a u substitution, let x minus y equal u, and then you can simplify the algebra very easily, and then plug in your limit. And again, because you're just letting any combination of x and y be 0, then you're not really caring about how you get to the origin, only that you get there. You can also just rationalize it in x and y and then simplify from there, because then you'll get the square root of x minus y, and you'll just be able to get the square root of 0, which is also 0. But these substitutions are important in terms of simplifying the problem, again, to one variable. And we're going to see other strategies like this essentially when we switch tripolar coordinates, which is another option that we can use. That's another way of trying to reduce our x's and y's to just a single variable. So different techniques may apply in different circumstances. Now let's look at a more typical example in two variables where things are a little not quite as nice as the first two examples. So in this case, we have essentially a fourth degree polynomial in x and y in the numerator, and a fourth degree polynomial in x and y in the denominator. And in this circumstance, there's not a nice way to reduce. We don't have a simple substitution that we can make. And so one strategy is that you can try various paths to the origin until you get something maybe that doesn't agree, or you can't think of another path. Now, the strategy of using the path examples, so you have to be careful, because if you don't choose your paths very cleverly, you're going to end up getting the same answer all of the time, and it still may not be defined. But the idea is, for instance, you can go into the origin along one of the axes. So if you let x equal to 0, then you end up, the x's cancel out, and you end up with just 0. If you let y equal to 0, again, along the x-axis, then you get something similar in that your numerator goes to 0, and you end up with this is identically 0 all the time along that axis. So the limit is 0. Now, you don't only want to consider the axis paths, you want to consider other paths. And so one way is to consider a linear path toward the origin. And we'll say more about why this path is a good one a little bit later in the video. But in this case, I'm choosing y equals not just x, but I'm choosing y equals kx. And the reason that I'm doing this is because this means I'm actually choosing any path along the origin. I could let k equal to 0 in order to go along one of the axes, but essentially I'm choosing a linear path to the origin, but it doesn't have to be y equals x. It can be y equals 2x or y equals 1/2 x, anything on a straight line going to the origin. And if you substitute this in for y, what you end up with, and what works really nicely here, is that you're able to factor out x to the 4th from both the numerator and the denominator, and then they cancel. And what you're left with is an expression in this case that depends on the value of k. So the slope of that line as you go toward the origin. That's not good. Because if the direction that you're taking toward the origin changes the value, then there's different values for the limit, and therefore the limit doesn't exist. So if I were to choose k equals 0, I would get 0. But if I were to choose k equals 1, then I would get 1/4, which is not the same as 0. And therefore, this limit does not exist. So even though it looked like it was going to be 0, 0, 0, we found a straight line path to the origin, proved that, in fact, it's not always going to be 0. Sometimes it's going to be some other number, and it's going to depend on the specific path that you choose. Now, sometimes I refer to these nice paths that actually we need to prove as critical paths. I don't think this is a particularly sort of formal term, but usually it's a path that's going to work pretty well for your choosing how to prove that the limit doesn't exist. Now, again, the origin is not universally the point where we will get into trouble, but sometimes it will be the point that we get into trouble. Now, this is an example. If we let x equal to 3, we can let the point that we're approaching, because we're going to 3, 0, this simplifies, and then we let the limit of just y go to 0, we get 3. If we let y equal to 0 first, and then we let the x go to 3, we also get 3. What if we try some other points? What about some other paths? So I tried x equals 3e to the y. When y goes to 0, this also goes to 3. So this is going to reduce my problem to a single variable. I've got 3. What if I let x equal to y plus 3? That is a straight line path, not to the origin, but to this particular point in the plane. What happens if I plug that in? I also get 3. This is a good sign that, in fact, the limit is actually 3. But you don't have to worry about the point like x plus y equal to -1, because that's not a condition that you have to worry about satisfying at the point 3, 0. So the fact that this is in the domain and not at the boundary kind of saves us from the fact that we might run into a particular problem. Now, if we look at one more example, again, sort of the polynomial, sort of the rational function example, we can also start this problem similarly to the previous example that we were looking at that was similar to this. We set x equal to 0, we got 0. We set y equal to 0, we also got 0. If we try y equals kx, that prove that the limit didn't exist in the previous example, we also get 0. As you can see, if you plug it in, you cancel out an x cubed, and then when you let x equal to 0, you end up with 0 over k squared. So regardless of what line you're going to, you end up with 0. But it turns out this actually isn't a defined limit, because this is not the right path to choose in order to actually see that it's undefined. And so this is where I'm going to talk a little bit about what I refer to as the critical path. Now, the idea is behind this is that we want to be able to simplify our expression as much as possible. And in order to identify that path that is going to potentially be the most problematic, we want to try to make the powers of our variable in the denominator the same power, because that's going to allow us to factor that power all the way out of the denominator. And then if it's going to cancel nicely, and we'll maybe get something which is not 0. But if we can't factor it all the way out, then we're going to have the numerator and the denominator going to 0, maybe at different rates. And so that will sort of deceive us into thinking that maybe the limit is actually 0 or some specific value, when in fact it's not. So here I'm going to try the path y equals kx squared. And again, if you've gotten 0 a bunch of times and you just try y equals x squared, you're probably fine. But I suggest this idea of this critical path so that you can actually just test this one path and simplify the amount of evidence that you have to show. You don't have to show that it's ever 0. You have to show that you can get 2 paths to the origin or to your point that you're interested in that are different from each other. So here, if I plug this in, I'm getting the x squared as my ideal path because I have a term in the denominator, which is x to the 4th, and a term which is y to the 4th. And if I set those essentially equal to each other, then I get the relationship between x and y should be y equals x squared. So that's why I'm using y equals kx squared. And again, k doesn't have to be 0, but it can be. And so if you plug kx squared in for y, what you find is that when you simplify, you get an x to the 4th in the denominator in both terms, and you get an extra 4th in the numerator in both terms. Then you can cancel that, and you end up with k over 1 plus k squared. And again, if you let k equal to 0, you get 0. But if you let k equal to anything else, you don't. If k is 1, then you get 1/2. And if k is 2, you get 2/5, and so forth. So because there's still a k left, and that can change based on the type of parabola we're using to approach the origin, we know that the limit doesn't exist. So again, that's the idea behind this notion of these critical paths. You want to set the denominator equal, the 2 terms equal to each other. Now, if you have multiple terms, what I would suggest is that, like if you have 3 variables or something like that, what I would suggest is that instead of trying to do it all at the same time, let x equal y or something like that, or y equals z, and reduce it to 2 variables and then proceed from there. We're going to talk about some other techniques you could use for the 3 variable case, but it depends on the kind of function you have as to whether or not that is available. Some of those other techniques are available or not. The path problem is always potentially available, but it's choosing those coordinates. If you have 2 components that are both x squared and one is a different power, then you can set, like if you have x squared and y squared, set x equal to y, but then use this idea of matching the powers for that remaining variable. All right, so this is another example And another strategy for dealing with some of these two variable problems is to switch to polar coordinates. Now, polar coordinates works best if you have terms in the denominator that have the same power. So essentially that path that we would have taken that would have established our potential issues would be y equals kx, so a straight line to the origin, because these are both the same powers. You can also essentially use polar coordinates to do the same thing, because if theta is left over when you're done simplifying, theta is essentially a straight line path to the origin. And so these are completely equivalent to each other. But the fact that this is x squared plus y squared means that we can reduce our denominator to just r squared. That makes things cancel nicely. And we replace x with r cosine theta and y with r sine theta. That matches up that r squared. And because I'm left with cosine theta, sine theta, I can say, since this value is going to depend on the angle of theta that I choose, the limit doesn't exist, because I'm going to get more than one answer. Now, for 3 variables, then I can use polar coordinates to reduce this to a 2 variable problem, and then again treat it similarly to the 2 variable case that we had before. In this case, I might let r equal to z as my third thing to see what happens. As my path in the rectangular coordinate, in the cylindrical coordinate system. But when I see something like this in my denominator, I may also want to think about spherical coordinates. But let's proceed along this r equals z path just to show that it is in fact, it is perfectly going to work here to cancel out the thetas. So in the previous example, we had only x and y in the numerator and a second power of expression in the denominator. Here we have x, y, and z. And so that's like a cubic polynomial in the numerator, but only a quadratic polynomial in the denominator. And so when I let r equal to z in this cylindrical version of the limit, I can then let the path go to 0. I'm going to end up with z squared canceling out only 2 of the z cubes in the numerator. And then I'm going to end up with letting z go to 0 is going to give me 0. Again, you can do the same thing if you, instead of replacing r with z, you can replace z with r. You'll get the same thing. It'll look a little different, but either way, you're going to end up with 0. So in this example, because the numerator is essentially 1 degree higher than the denominator, then the numerator wins. Essentially, when you go to 0, you actually go to 0. It doesn't matter the path that you choose. Now, you can also do this, as I said, with spherical. Now, if you haven't been introduced to spherical in your course yet, then don't worry about this, but this is also an option. The idea here, again, is to cancel the rows, but you can make one substitution instead of a double substitution. So here, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi, and then x squared plus y squared plus z squared is rho squared. And so again, phi and theta, if they're left over, that's like having a theta left over in the 2D case. That means that the angles that you're taking to the origin change the value of the limit. If there are no phi's and thetas left over, then it doesn't matter, and the limit is always the same. And we get a similar effect here. The denominator is rho squared, but x, y, and z all have a rho in them, so that's a rho cubed. And so even though these things are left over, when I cancel the rows, I have a rho going to 0 left in the numerator. And so what these values are doesn't make any difference. I get 0. So this limit does in fact exist, and the limit is 0. Now, again, these problems can be somewhat tedious to work through, particularly in spherical coordinates. They do end up canceling nicely if they're going to cancel, but you do end up carrying around a lot of these sine phis, cosine phis, sine thetas, cosine thetas, and things like that. And so the expression can look large and awkward without necessarily being a problem at the end of the example.